Welcome to EDU World Space.
Our goal here is to start with conservation of energy for two particles interacting via gravity, and then convert that into center of mass coordinates. So just to set up the coordinate system, we are assuming that the center of mass is at the origin, and R1 and R2 then are going to remain along a line. And what we mean by R without the subscripts is it is basically R2 minus R1. So it is the separation vector between the two particles between M1 and M2, which is exactly what you need for particles interacting via gravity. But the conservation of energy is simply put sum of kinetic energy. So each particle has its own 1/2 mv squared term. And then gravity is an interaction, so it is going to be just one term with the difference between the two particles' positions coming in the denominator. Potential energy of gravity is negative because it's attractive, negative g m1 m2 divided by the difference in the positions and the magnitude of that. So it is a scalar quantity. So a couple of things. We could go through the details of calculating the center of mass vector R, but simple center of mass definition gives us, and it's shown as equation 2.23 in the book, R1 position vector in terms of R is equal to minus reduced mass M1 R and a similar equation for R2. Except it is positive R. So the other thing, of course, is the definition of the reduced mass, which comes about by calculating the center of mass coordinates. And I do note that if mass 2 is much larger than mass 1, for example, then basically R2 is 0. You're at the origin. And your reduced mass basically turns into mass 1. So reduced mass is basically important if you have masses that start to be equivalent in size, which could happen in binary star systems. Anyway, do note that R2 minus R1 is indeed equal to R if you put it all together. That is a good thing to note. So in order to get into the kinetic energy, now that means that the potential energy term is very simply put, if we can rearrange the M1 and M2, the gravitational potential energy is equal to minus G M1 M2 over R magnitude. And since we're going into center of mass coordinates, we probably want to look at M1 times M2 cross multiplying is the reduced mass times M1 plus M2, which is the big mass in the system. Big M stands for the basic mass of the system, everything in it. So our gravitational potential energy looks like minus G mu big M over R. And we've done that term. To do the kinetic energies, what we need to do is take the time derivative of 2.23 and 2.24 and then turn those into v squareds. So let's just take 2.23 to begin with. R1 dot is equal to minus mu over m1 r dot. And then R1 dot squared is equal to, let's just square everything on the other side. And R vector dot squared is just v squared. It's the mutual motion of the two objects about each other. And we can do a similar thing with R2. Take its time derivative. And it gives a very similar expression. Except the quantity out front is mu over m1, m2, sorry. Okay, and so then, and R1 dot, of course, is V1 squared. R2 dot squared is V2 squared. So now we're ready to replace into the kinetic energy. It's equal to 1/2 m1, and now we're going to substitute in the expression for V1 squared. And we'll do the same with the second term in the kinetic energy. And then it's a little bit of an algebra to go about simplifying the kinetic. Whoops, I want to use just plain ink here. Okay, so we have a common thing of 1/2 mu squared, v squared, and then 1 over m1 plus 1 over m2. And it should be noted that this is the same as 1 over mu. Kind of like adding resistors in parallel, which is kind of the idea. Masses are behaving in parallel. And yes, so the kinetic energy is 1/2 mu v squared. And we have basically shown that the energy goes as 1/2 mu mutual velocity squared minus g mu m over r.